Right, our last speaker for today, tonight, and the next day, covering all the time zones, is Jaganmoy Jodder, who is a postdoctoral fellow at the Evolutionary Studies Institute at the University of the Witwatersrand. So go ahead, Jaganmoy.
Good evening to all. And it's almost closer to midnight here in Southern Africa. And thank you for sticking throughout the sessions today. And it's a pleasure for myself and my colleagues listed here to present in this wonderful conference. As you can see, this is the possibly only time window that we know of now from our own existence that do show possible evidence of life. Most importantly, there are life, and maybe more important life, which are also existence. And then there are these glimpses which are taken from the International Space Station, a night view of our own Mother Earth. And the point of today's discussion is how our own modern Earth was different during the Archean. And to address few of these questions and to answer some of these aspects related to early microbial life, we will take you through a deep journey into our Earth's history. So what is the Archean? So this is a time scale of the early Earth history where you see the different time periods, mostly the time periods considering the evolution of our own stellar system, solar system. And the time period here today in discussion would be the Archean, mostly roughly from 3.5 to 2.5 billion years. But if we have to look and dig down into the Earth's history, which is shown here in this spiral of the Earth's evolutionary history, where do we find this? It's exactly here, and very, very, very far in the spiral of our Earth's history. We will be looking at different possible early Earth processes, also evidence of putative microbial life from the Earth's ancient history. And now when we talk about the Archean Earth, how the Archean Earth is all about, what the Earth is all about, we would like to emphasize on the fact that the Archean Earth was as beautiful as Mona Lisa's portrait here, but it becomes difficult to reconstruct the history, as you might consider that if this portrait of Mona Lisa would have got old over time, and then if this same portrait you would want to find out some crucial details, as in if this portrait would have got crumpled or compressed in a way, and you would want to reconstruct the history. This becomes a very daunting task, and that's how I go about the fact that the Archean history is a very difficult challenge to unravel. Nevertheless, when we talk about the Archean, what is the Archean Earth? And to answer that, we have here an artist's impression of what the Archean Earth is all about. Now, the Archean Earth, as we know of today, mostly was full of volcanic eruptions, which led to gases such as carbon monoxide, sulfur dioxide, any hydrogen sulfide, and several different gases that contributed to the atmospheres then. And there was a strong absence of ozone, which means that this lack of ozone layer did really aid into the radiations such as harmful radiations here, such as UV, to enter Earth at a very regular space or intervals. Moon was much closer than what we have on our modern Earth. Our moon was much closer, that had different impacts on the tidal activity, and the bolide impacts such as meteorite showers was very vigorous, and there were events of that were also recorded on our early Earth's history. But foremost, the most important ingredient for life is water, and which was prevalent on our early oceans. And this is how we go about discussing about the earliest history of our Archean time. But why and how do we know that life did exist during the Archean, and which are this evidence? And how do we know that life did exist, and how does life look like? What are life overall, and why would one go and where would one go and find this evidence? So the Eoarchean or the Hadean time period is very scanty. Also, the rock record are not very well preserved. So for today's discussion, we will be only highlighting the Archean time, mostly from 3.5 to 2.5, as I've mentioned already. And the window here presented in this slide is the Paleoarchean. Why I show this is of its recent discovery by a group of scientists who argue to have found the oldest evidence of methanogens or filamentous-like bacteria, and these are these filament-shaped, needle-shaped bacteria of very, very tiny diameter, close to about 1 microns, and very tiny. Our hair follicles are much thicker than that, but this you would only be able to see under the microscope, and these are preserved as in segmented filamentous microbes. Most importantly, one of these microbe was studied under the 3D conofocal Raman spectroscopy, where it produced this imagery where it shows the distribution of the different carbonaceous kerogenous particles in this 3D dimension. And that's how we go about the first evidence of mostly the recent evidence of a very unique life that harbored subsurface environment, mostly hydrothermal vent systems, which were once existent during the Archean. Now the question is, if you are lucky, then you will find them. But the fact that it is a very big mission in itself, and it's a hunt for a needle in a haystack. And this is how you might want to go about this kind of things, because it's never easy to find microfossils from that ancient rock record, and it's always a mission, and it's always a difficult one. So, but when we talk about this kind of missions, you really have to undergo field trips and field missions or excursions where you would want to visit places on Earth. And these are unique localities because our Earth is very dynamic, as you know, and because of modern plate tectonics, you would hardly preserve some remnants which are of the Archean age. But there are some time windows, and these time windows are from Southern Africa, from India, which will be discussed a lot because this is also where we have discovered the oldest microfossils, which is a part of our research, current research with our group. And then we would also show you some evidence of primary life from the Pilbara Craton of Western Australia. So this would form a core component of today's discussion and how life is preserved in some of the Archean record from these three places of our modern Earth. Now, when we talk about life and bring the concept of life, we also have to familiarize with the fact that where and how and which settings life did exist. And the time window here is Paleoarchean, which is a very unique window during the Archean Earth. And why I say this unique is because of the fact that most of the Earth was covered by magmas, but very importantly, these magmas were submarine in nature, meaning that when you have eruptions, always mostly under submarine settings. And this is a photo taken from the Hawaiian island to just show you a comparison of how the Paleoarchean Earth look like. So 70% of the Paleoarchean greenstone sequence or volcano-sedimentary rocks that we know them as are made up of submarine volcano-sedimentary rocks, mostly submarine volcanic rocks. And to the right is shown a photograph of a fossilized feature of a rock type, which is very diagnostic when you see them in the field. These are nothing else than pillow lavas, which are created because of the mixing of magmas with the water column. And this creates some bulbous spheroidal features and also resemble pillows. And that's how they are named. This name is derived as pillow lavas. More importantly, these greenstone belts are very unique because they are of Greenschist facies metamorphism, which means that they are of low strain and low metamorphic grade, and they have undergone relatively very, very, very minute deformation. And this together with volcanic rocks, the most important rock type of today's part of discussion will also be cherts. And what are cherts? Chert are silica-rich rocks where you have this banded black and white nature of chert, which is largely the alterations of silica-rich band and carbonaceous rich bands, and this will form a major part of today's discussion. When we move from the Paleoarchean time and we move further ahead in time, when we travel to the Meso to Neo-Archean windows of our Archean Earth history, we have a setting which is slightly different than the Paleoarchean. And why I say this is because of this nature of the lavas, which now are mostly subaerial. And when we say subaerial, it means that the lavas float mostly on the surface of our Earth, and which created these beautiful textures, which are also called as ropey lava flow or pa hoi hoi. And if you are lucky to come across these textures or features, if you happen to visit South Africa, India, or Australia, you will come across these fossilized, ropey, hoi features in the field, and you would be wondering how our Earth was then. But more importantly, the Earth, together with the subaerial lava flows, was comprising of some volcanic sedimentary rocks, which are mostly sediments such as sandstones and minor carbonates with iron formation. Here also the grade of metamorphism and the rocks have undergone very low strain and relatively lower deformation and low grade grainaceous phases. So which are excellent spots to study early Earth surface processes and also to look for any trace of life. Now, once we talk about Archaean Earth and the history of the early part of Archean, which is Paleoarchean here, the most investigated piece of earth or piece of rock assemblage from our own Mother Earth comes from Southern Africa. And here it's the Volcraton, which is shown here in the map with an inset. And this is the geological map of the Barberton Greenstone Belt, where there are different colors. And I will come to the point which colors means what. So this is a slice of different rock units. And if you want to imagine yourself having a cake with the oldest rocks and stacked up by the youngest units, so this is how you would come across if you want to cut a piece of this mountain belt and would want to see the rocks sitting on top of one another. So the lowermost part is the Onwarwak group, which is largely made up of mafic to ultramafic volcanic rocks shown here in this geological map. The other part are the sediments, which are shown here in slightly light green color from the fig tree. And the younger-most unit are mostly Moody's group, which are shown here in yellow colored portions. So these Moody's are the youngest unit of this Barberton sequence. And nevertheless, we have many different granitoids of different ages that are all intrusive into this volcano sedimentary sequence. Now, the Barberton Greenstone Belt is also very unique because of this fact that the World Heritage Site was declared by UNESCO in 2018. And if you happen to visit South Africa, please do visit Barberton because of its unique geology and the set of different evidence of early Earth surface processes, microfossils that will be discussed today. When we move down, further down of Barberton Greenstone Belt and move further south to the non-veiny Greenstone Belt, we have the most undisputed evidence of life. This comes in the form of stromatolites, which are mostly domical in nature, and these are the structures that are created by microbes. The microbes, once they inhabited the earliest shallow part of the ocean, they would still use the sunlight, and with that they would trap or bind the sediments, and they used to do this using this energy of the sun, and they would create this kind of microbially induced structures, mostly organosedimentary structures, and they are preserved very well from the non-veiny greenstone succession, which are Paleoarchean in age. And these are the oldest stromatolites of the African continent and probably one of the oldest of its kind on our Earth. And if we move younger into the time period, if we move to the Mesoarchean time period, where we see is also likewise slightly similar, but more conical stromatolites, which are also organosedimentary structures produced by microbes that were using the sunlight and also occupying the shallower part of the ocean here and probably creating this kind of structures, which are fossilized now. Now, this stromatolites from the Pongola supergroup are much younger, of 3.0 billion years, roughly 3,000 million years in age, and they are further east of the non-veiny greenstone belt, which is shown here in the map. And it's beautifully exposed in the White Amphalogy River area. Moving from South Africa to Australia, and if you take a flight to Perth and move further north of Perth, what you would come across is an ancient Archean granite greenstone terrain with Mesoarchean tectonic cover successions, which are shown here in this geological map. So the East Pilbara terrain mostly will be discussed here, which is largely made up of greenstones and intrusive by granitoids, and the Fortescue group, which is also a much younger unit from the Meso to New Archean time period, preserves different bona fide evidence of stromatolites. So the first evidence comes from the East Pilbara terrain from the Dresser Formation, which is roughly 3.5 billion years in age. And these are conical structures, also microbially induced, and they are remnants of one of the earliest primary life forms, also from our shallow part of our oceans. If you move younger in the time scale and we look into the window from this Fellipool formation, we would come across some crinkly layered laminated structures that are also conical, and they are also stromatolites, and they are of 3.3 billion years in age. And if we move younger into the time period, we would come across the Tumbiani formation from the Fortescue group, which are of 2.7, and these are very diverse examples of stromatolites coming from the early Earth during the Archean. And if we happen to visit India one day, if you would be in the East Indian Shield, you would be visiting states of Odisha and Jharkhand, where you would come across the Singhbum Craton, which is situated in these two states. And there you would come across volcano sedimentary rocks, which are also colored here in lighter green and also deep green. So this is the area where I conducted my PhD. I spent a lot of time here mapping this greenstone sequence, which is also well known as the Diataric Greenstone Belt. Also, I just studied the Koirumi-Sani Greenstone sequence, which is exposed further north of the Singhbum supracrustal. And here, if you happen to visit in the central part of the Singhbum, mostly it's all granitoids which are intrusive into this greenstones, and the much younger rocks are shown here on the margin of this greenstone terrains. These are the Koira group rocks, which are of Mesoarchean in age. And if you happen to visit the Koira Valley, you would come across beautiful stromatolites, which are also layered structures, and they are also microbially induced, and they are of 3 billion years. And sometimes you are very lucky to find remnants of carbonaceous matter still preserved in these crinkly layered laminas, and you are very fortunate to find them in different places from the Singhbum Craton. Then you would be very happy to do some analysis on these very primary structures. So now that you have visited some places virtually and you have wandered around some field localities from the Kapval Craton, where you have found the oldest stromatolites of 3.4 billion years, then you have the oldest undisputed evidence of stromatolites from the Tres Formation, which are from Pilbara, and that you have visited the Mesoarchean sequence of the Singhbum Craton, you have stromatolites all across this continent. Then you would want to visit Shark Bay area in Australia. Why? Because you want to see the modern day equivalents, because these are our modern day stromatolites which are still there and pretty much there. If you want to have a swim close to them, they would be there, and you would kind of wave to our modern day cyanobacteria which are forming these domal patterns. Now, moving from more megascopic to more microscopic scale, what we preserve in the Archean is very unique. And why I say unique is because of the fact that the different association of rock, which are very, very different from different, and also will be discussed throughout this talk. So this is one sequence from the South African Kapval Craton, and which is most famously known as the Barberton supergroup, close to 3.5 to 2.2 billion years. And these are the oldest rocks, as I've shown you the layered cake stratigraphy. But here we would be emphasizing on the Buck Rift and the Kronberg formation overall to look for any microscopic evidence of life. Now, where and how to find this evidence of life? You would have to investigate the chert horizons, as I've mentioned, that they are very important in that aspect because they are comprising mostly of silica and carbonaceous matter. And if you are very fortunate, you will come across structures which are all microfossils. So the first evidence that I provided in the beginning of our presentation was filamentous microbial life that probably harbored during the Archean close to hydrothermal systems, and these are chemotrophic in nature. Other than that, there are also examples of this nature. This is a solitary spheroid, which is lenticular in nature, and these are mostly made up of silica and carbonaceous matter, but the distribution is important here to understand, and also the shape of this microfossil, which will be also discussed later on in today's talk. Because of the tapered edges or the appendage being so flared out, why is it important and how it connects to the later part of the story. Now, talking about microfossils from the Kronberg formation, there are also cocoidal-like microfossils, possible remnants of cyanobacteria, and this has been discussed by different authors, and they are also preserving some carbonaceous matter within their structures. So these are some of the benthic forms of microbes, some planktonic forms in the form of spheroidal-shaped microfossils, and some chemotrophic microbes that I've presented from the Barberton Greenstone Belt. Now, if you happen to visit India and the Singhbum Craton, and if you would want to investigate the Padam Pahar supracrustals, which was a part of my PhD thesis. And I constructed this lithostratigraphic column with my supervisor Axel, who was also an investigator of this project from the Singhbum Craton. And we did investigate these rocks in ultimate detail that we were able to reconstruct the stratigraphy. But most importantly, we would be only highlighting the Tomka chert, which is again a chert unit mostly made up of silica and carbonaceous matter. And again, if you are very fortunate, you will come across reworked microbial mats that are entrained in some siliceous carbonaceous matrix that are crinkly layered and mostly made up of carbonaceous matter. And these are remnant of some benthic microbial life from the Paleoarchean time window of our Archaean Earth's history from the Singhbum. And more importantly, and very surprisingly, we have our friend here again, which is the lensoidal spheroidal microfossil from India, the oldest of its kind. And this is our discovery from the Singhbum Craton, which are mostly made up of carbonaceous matter and some silica. But the interesting aspect again here is to point that they are also having the tapered, flared out appendage close to the extremity of the spheroidal nature of this microbe. Other than that, they have also smooth walls. Sometimes they are irregular, but they appear to be discontinuous. And most importantly, sometimes if you have microbes of this kind, if you are very, very fortunate, then you will have some cusps or doublets of this nature, which will be joined to one another, and they also have the flared out appendages. Moving from India to the Paleoarchean window of Western Australia, we would investigate the pile of volcanosedimentary rocks from the Pilbara supergroup. And very importantly, again here, we would investigate the Strelipool chert, which is a chert unit mostly made up of silica and carbonaceous matter. But more importantly, they do host evidence of life. And life, as we know, and we have presented in terms of solitary spheroids, they are these spheroids which are typically 30 micron in diameter cross, and also they have this very diagnostic feature of tail-like appendage. Sometimes they do have an irregular wall boundary, but then they are also crooked or sometimes not, sometimes broken. But other than the Strelipool chert microfossils that are 3.5, 3.4 billion years in age, what other microbes have been described? The ones that have been of high discussion and for a long time, scientists have been working on the apex chert microfossils, and it was discovered by William Schaff in 1990s, where he described these filamentous microbes within the chert unit, and these are one of its oldest of its kind. Now moving from the Paleoarchean window and moving into the Mesoarchean, what do we have in terms of the catalogue of life that we preserve from the feral quartzite unit? So this is one fossiliferous unit from the Mesoarchean window of Western Australia. Here you see the feral quartzite stratigraphic column from the oldest to the youngest. And if you want to investigate some of the chert units which are black in nature, you would see this kind of fossils. And they are possibly lensoidal microbes, which are shown here at the topmost part of this photomicrograph, which is also shown here at the bottom part of this slide, where we have a Raman spectroscopic image, and the Raman image exactly shows how the distributed carbon is in this structure. And the bright yellow fringes are a representation of the carbonaceous material, whereas the darker fringes are mostly representation of the silica. So this is one lensoidal spheroid, solitary, but then again you have colony of lensoids and spheroids together forming ellipsoid, forming a globular pattern. And this is very startling and very interesting to study. So we did study on in terms of Raman spectroscopy, we did found the carbonaceous matter distributed throughout the structure of the spheroids or lensoids. They are distributed throughout these microbes, and this is one of our recent study from the Australian counterpart of the Mesoarchean time. Now, I have always mentioned throughout the talk for these planktonic forms to be important, and also their importance of this tail-like appendage. And very recent study confirms that, or rather they argue that this tail have been of huge utility. When I say that, it means that this tail-like features were rather used for movement. So probably these planktonic forms were at some point escaping some environments because they were attacked by some predators, or maybe they were trying to find some new home or new ecological niche. Because of this fact, this tail-like appendage did really help them to move from some different points in the oceanic water column. That's how important the tail-like appendage is and the structure overall with the taxonomy. That's what I was mentioning earlier. And moving from sporoidal microfossils, if we have to investigate the Syngum craton again for its unique preservation potential, this is a recent discovery from the Koira group of the Syngum craton, where there are volcano sedimentary rocks of Mesoarchean to Neo-Archean age. And we would likely to study the Noa Mundi formation of the Koira group, where you have coil-shaped cyanobacteria-like microfossils, which are shown here to the right. And these are possible remnants of some 3 billion-year-old cocoidal microfossils from the Syngum craton. And if you're lucky, you'll come across some cell division, which are still fossilized, and some different cells which are of different sizes. So the climax of today's talk is why the Archaean, and here we have some of this very important and interesting question: why the Archaean time period? So as you can see that the Archaean was very special, and as I've mentioned that the Paleoarchean to the Neo-Archean holds different clues in terms of different life and structures that are preserved in the on the Earth. So you see there are different evidence of microbial metabolic pathways that have been mentioned and discussed and discovered by different authors of the time. But the other aspect of the Archaean that I would like to highlight here is that our Earth today is very different and unique because of the fact that we have oxygen on our modern Earth. But it was not the case when it was this time period that is shown here. Probably oxygenic photosynthesis or the advancement of oxygenic photosynthesis started close to 2.9 billion years. And it was a time which was very unique because also the oxygen was only available to the shallow part of the oceans, but not in the atmosphere. But close to about 2.5 billion years, we have considerable increase of oxygen in our atmosphere. Of course, not considered to our present day atmospheric levels, but still much more than what we had in the past. So with that, there are these facts that what we have seen that the Archean Earth was hugely diverse and booming with life, with different evidence that I've provided us throughout this presentation, that there are lensoidal-shaped microfossils, mostly made up of carbonaceous matter, cocoid-shaped microfossils, and then there are filamentous microbes, which are representation of some microbes inhabiting some subsurface environments. There are microbes which were possibly linked to one another, and then there are diversity in life that you may come across. But more importantly, the link to the oxygenic photosynthesis happened with the advancement of cyanobacteria. And this cyanobacteria, as we know of the more megascopic structures that we have presented from today's talk in terms comes from stromatolites. So with that, I would want to coin this fact that we say that the Archean is special because we see a huge insurgence of biology. And this insurgence was close to about 1,000 million years history of our ancient record. And of course, the conditions with oxygen did not happen overnight, and it did take place over this 1,000 million years of our history. And this was a very, very slow transgression, but it did happen. And then the Earth, what we see now, is very different because of this biological insurgence of the revolutionary processes in metabolic pathways that we come across all across during the Archean. So with that, I welcome you back home. And if you were or we were to look for life elsewhere in different planets such as Mars, or it would be the Enceladus, we would have to investigate our own planet Earth because of the fact that it does preserve these diverse ecosystems. And we do have now seen that how diverse and how dynamic the early Earth was. So the early Earth, as I've mentioned earlier, was bombarded by meteorite showers. There were high intense UV radiations and with no ozone and high immense volcanic eruptions with volcanic gases, but there were life, and life was pretty much abundant, as we know from today's presentation, in the form of stromatolites, which did occupy the shallower part of our oceans, probably because of the benthic nature. And of course, when we move down to the deeper part of the ocean, there are lensoids and spheroids, which were using their tail-like appendage to swim across the ocean and to move from one place to the other, maybe for escaping some predators, which we don't know. And also there were diverse ecosystems close to our hydrothermal vent in the subsurface. So there is this coexistence and coevolution of life during the early Earth with the Earth itself. And that brings to a very interesting fact that life evolved and thrived under these diverse conditions and these diverse ecosystems. Life was abundant. But the other question that we can one ask to each other today is that did life really cooperate in terms of what we know as cooperation behavior? Maybe it did. And then these different ecosystems favored for different lives to have cooperated in different behaviors. Now with that, I would like to leave and thank all of the sponsors that have helped us throughout the years for this research and our group especially. And I would like to thank this committee and the scientific organizing committee of the LITU conference for inviting us and to present this at this conference. And with this small message, I would like to leave that if elsewhere we were to find life, it would be on our own Mother Earth that we would have to look and introspect in terms of different kinds of life forms that we still may have to search, and we still are, behind some research. So thank you, and I hope that you will enjoy the rest of the talks and sessions following up to tomorrow and day after tomorrow. Thanks.
Excellent, thanks, Jaganmoy. So that brings to a close our day and evening, late evening for some people. So that brings an end, and that brings an end to the day of the past, as far as the past goes for this conference. Tomorrow we'll be dealing with the present, and the next day with the future. So I don't think there are any questions on here. David, do you have anything to say?
So I know Jill did have a question on the some of the dates on the slides for the stromatolites, for instance. You didn't show error bars, and she was just curious how accurate that was.
Sorry. Oh, let me go back then.
Oh, I see. Yeah. So Jaganmoy, Jill is asking, there are no error bars on the dates on the slides of the stromatolites. So how accurate are they?
Oh, yeah. So because of the fact that this is a very nice question, I mean, we would not be able to accurately date these stromatolites because these are all, sedimentary rocks which are devoid of some dateable material. But what we know of the dates are units such as the ones as if I go. So if we would want to date some of these rocks, we would be willing to date some material which is dateable. Let's say if it is zircon or if any other material, but then we would not be able to find them in the stromatolites itself because they do not contain those detritus zircons, most likely. But what we would date is the overlying and the underlying rock. And if you would lucky, maybe you will come across some ash layers within these units, and then you will be precisely dating them. But yes, for sure, what we date are the overlying and the underlying units, and which gives us the roughly time period of these stromatolites overall. So that's why I mentioned rough ages of roughly around 3.5, 3.4, 3.47 or something. Yeah, something close to that time. But the precise, how much of precise this is, yeah, that's a question, because nobody, I at least I'm not aware of geoscientists who have dated stromatolites. Maybe in the future we will look for detrital zircons in some of these units, which I'm not sure if there would be. But let's hope that there would be some zircons to be able to date them more precisely.